Hello, we are doing coding demos for Indiana State Computer Science, and for this video we're going to look at the halting problem. Halting problem is a famous problem in computer science where you're trying to figure out whether a given program will ever halt or not. Okay, so we're going to do this in two parts. This video we're introducing the problem and looking at the structure of the proof, and then in the second video we're going to do a reading of a proof in verse in the style of Dr. Seuss, which is pretty cool. But before we do that, we want to make some sense of what's actually going on there. Okay, so the halting problem, and here's a link to the Wikipedia page about the halting problem. So what's happening there is you have some kind of program. So here's a program, and the question is, does this program go into an infinite loop, or will it eventually halt? Okay, so for this code right here, it definitely goes into an infinite loop. That's easy to tell. And then for this program here, it's very simple. If you ran that, it definitely does not go into an infinite loop. But the goal is to be able to figure this out for any program. So what if you have a program that's 1 million lines of code, and there's all kinds of loops inside of there and functions calling other functions and very complicated? Are you going to be able to figure out whether that very complicated program goes into an infinite loop or not? That's the question, and that's called the halting problem. And it turns out that this is impossible. That very many programs you can tell, but there's always going to be something complicated that you can't quite figure out. And there's a mathematical proof of this, and we want to look at how that proof works so that you can perhaps better appreciate this version of the proof here. Okay, so I have the basic structure of this proof right here, and we're just going to sort of talk through it. Okay, we're claiming that the halting problem is not solvable. Okay, we're going to prove it by contradiction. What happens with proof by contradiction is you're going to assume something. So we're going to assume that you actually can solve the halting problem, and then come up with a contradiction. So you come up with something that cannot possibly be true, and that would show that what we assumed cannot be true. Okay, so let's just go ahead and assume that we have some program P that solves the halting program. So no matter what program you give P, it's going to figure out whether there's an infinite loop or not. This is the behavior then. You give P, this notation here means you give the program P some other program to check and an input for that program, and P is supposed to tell us whether this program with this input halts or not. If this program with this input never halts, P is supposed to say bad. If this program running on this input stops eventually, then P is supposed to say good. So now we assume that this P exists, and we're going to try and come up with a contradiction, something that implies that this actually cannot be. All right, so first step, we're going to make a program called Q. So this program Q, what we're going to do, it takes some input A, which we're going to think is a program. So it could be R code or Python code, or it could be Microsoft Word, whatever it is. It's some program that we can run. And what Q is going to do is it's going to ask P, all right, run this program P, and say, if I ran this program A and I gave A itself as input, what would happen? Would it halt or not? Now for most programs, probably this would result, if you took some random program and gave itself as input, probably the program would say that's bad input and halt. So what if you try to run Microsoft Word with Microsoft Word as input? Well, Microsoft Word would probably say, that's not a document, I don't understand. Okay, but so we're thinking of this in terms of all possible programs A. And so if we give A some code to Q as input, then we're just going to see, does it halt, yes or no. All right, if P says that it was bad, then we're going to stop. Okay, so if A does not halt, Q of A does. If P declares that A was good, then Q is going to go into an infinite loop. Okay, so to sum up, what Q of A does is the opposite of A of A. So if you run A with itself as input, Q is going to give the opposite effect. If A of A does not halt, Q does. If A of A does halt, Q does not. Goes into an infinite loop. Okay, now let's see what happens if we run Q with itself. And you might actually try to figure this out on your own without reading through my notes here. What's going to happen with Q of Q? If you run Q with itself as input and you plug it into this right here, is it going to halt or not halt? So that's the question, and we're going to come up with the answer is it's going to halt and it's not going to halt, which it can't possibly do. But see if you can work that out yourself. Just pause the video, think about it. Okay, now we're going to go through it. All right, so what we want to do is just take the definition of Q here and plug in Q to see what happens. So the first line of code in Q is we want to ask the P program whether Q of Q halts. Okay, so we're inside of Q, and then we're going to ask if Q of Q halts. P is going to give some answer. It's going to be bad or it's going to be good. So this result here is either bad or good, and so then we can see what happens. So what if P of Q said bad? All right, so the definition of P is this. If it says bad, then it must be that the program given to P does not halt. Result is bad. P's definition says that Q of Q does not halt. All right, now what does Q actually do in that situation? That would be this line right here. So Q actually does halt. Right? You run P, ask it whether Q of Q halts, and if it does not, if it says bad, then we are going to halt. So that can't be, right? So this is telling us that Q of Q halts, does not halt. That's saying that Q of Q does not halt if this program P is correct. But this here says that it will. All right, so it cannot be, then we know that this doesn't make sense. We can't have this result coming out bad, because if the result comes out saying bad, then we would have that Q of Q actually, it doesn't halt because that's what P said, but then it does halt because that's what we do right here. Okay, so now what if the result said good? You reason through that. If the result said good, then that would mean that Q of Q, because that's what we asked P about, does halt. So P reports good, that means Q of Q does halt. But then if we look at the definition of Q, when it gets good as a result, it's going to go into an infinite loop. So if P says that Q of Q is good, then actually Q of Q is going to be bad. All right, in either case, we come to a contradiction. That we have Q of Q does not halt, but then it does also, Q of Q does halt, but then we make it not halt. And so we're sort of designed Q here to do the opposite of what P says it's going to do. And so it must be that P is not correct somewhere in there on one of those inputs. Okay, so this is our proof by contradiction. And if you want, you can pause and kind of stare at this a little bit longer, or you can go over here and click through links. So in the next video, we're going to do a reading of this. Of course, you can read it on your own, but we'll give you a video reading as well. Okay.